In section 4.1, we study exponential functions and continuous compounding. That has to deal with money. So in this section, we're going to discover the properties of exponential functions by examining their graphs. We'll review the algebraic properties of exponents. We'll solve exponential equations, discover the natural base by examining a certain special limit, and review compound interest and continuous compound interest. And then we'll compare interest rates by calculating what they call the effective interest rate. So let's get started with the exponential function. So this is a function in the form y equals b to the x. And b is called the base. There's certain restrictions that we have on this base. First one is that it has to be positive, so it has to be greater than 0, and the base cannot be equal to 1, because 1 to the x is just 1, and then that's not exactly what we're looking for with this characteristic of the exponential. Now, the thing that makes this an exponential function is noticing where the x is. So x is in the exponent. And that's why it's called an exponential function. Now, why do we use the exponential function? Well, the exponential function is used to model functions or situations where future value depends on current value. For example, population growth. That's a good example. So basically, the more people you have, the more little people they have. And so the population of a county, city, country, whatever, the future value of that population depends on what the current value is because of reproduction, etc. And on the same token, you can also model certain other things like spread of disease, money investments, and also a little chemistry with radioactive decay. All right, next I want you to go ahead and do the exploration from the GeoGebra link that was provided to you. Answer these questions, and then we'll pick up the lecture after you finish that exploration. Let's review the properties of exponential functions. For exponential functions in the form of y equals b to the x, with b greater than 0 and not equal to 1, the function has the following properties. Number 1, it is defined and continuous for all x from negative infinity to infinity. So that means you can put in any number you want to for the x. Number 2 is positive for all x on negative infinity to infinity. That means the graph of your basic exponential function is always above the x-axis when you graph it. Number 3, we have a horizontal asymptote at y equals 0. That means it gets closer to the y equals 0, the x-axis, on one side. We'll get to that here in a moment. But it's only a one-sided horizontal asymptote. And number 4, it has no x-intercepts. And so it's always above the x-axis. It never actually hits the x-axis. And it has a y-intercept at 0, 1. Well, where does this come from? Well, if you actually put in 0 for the x, b to the 0 power is 1. So it's just 1, 0, or 0, 0, 1. And now for properties 5 and 6, this is where it depends on what the value of b is. So if b is greater than 1, that's sort of the break point for all this, then we have in behaviors that is on the left side. As x goes to negative infinity, it approaches 0. That's the x-axis. And on the right side, it approaches infinity. And then property 6 says it's increasing for all x. So if the b is greater than 1, then the graph looks something like this. It does go through 0, 1. It has a horizontal asymptote on the left side, and it gets closer and closer to the x-axis as you get further and further to the left. But on the right side, it increases to infinity. So recall that when we talked about rational functions that were a parabola over a parabola, we said that it has the same horizontal asymptote on both sides. Well, this is an example of a function that only has one horizontal asymptote on one side, and the other side goes to infinity or negative infinity. So this one's going to infinity. Now, for a base that is between 0 and 1, think of it as sort of a decimal base, then we have the following situation. It still has sort of the same in behaviors, but they've been flipped around. This time on the left-hand side, it goes to positive infinity, and on the right-hand side, it goes to 0, and it's decreasing for all x. It does still go through 0, 1, but it is the decreasing function. And now its horizontal asymptote is on the right side. All right. Let's review the rules for exponents real quick. So property number 1, b raised to the m over n power is the same thing as the nth root of b to the m, or the nth root of b worked out, and then you raise that quantity to the m power. Number 2, b to the 0 power is equal to 1, as we mentioned before. Number 3, b to the negative n is equal to 1 over b to the n. So if you change positions in a fraction, you change the sign of the exponent. Number 4, b to the m times b to the n is equal to b raised to the m plus n power. So you add exponents when they're multiplied with two different base. So I think of this as base, exponent, add the exponents. Now if you have base, exponent, exponent, then you multiply the exponents. So b to the m then raised to the n power is b to the mn power. Number 6, a times b, quantity raised to the n power. The n can be given to both the a and the b. So you get a to the n times b to the n. And the similar property for division happens. If you have a over b, quantity raised to the n power, then you get a to the n divided by b to the n. And finally, if b to the x is equal to b to the y, then x is equal to y. All right, let's simplify some of these using these properties, and we'll be as verbose as we can so that we can illustrate all of these properties. The question asks for 3 to the 7th times 3 to the 9th divided by 3 to the 6th quantity cubed. So in the top, we have 3 to the 7th times 3 to the 9th. Since we're multiplying base exponent times base exponent, we add the exponents. So this becomes 3 raised to the 7 over 9. And then in the bottom, we still have a 3, and that is raised to the 6th and then to the 3rd power. So we multiply the exponents, and we get 3 to the 18th power. Let's simplify by finding the sum of 7 and 9. That's 16. And then there's a couple of ways to do this. Technically, based on our rules, you should do it this way. You should say, well, since I'm dividing, I really take 16 minus 18. And now this is equal to 3 to the negative 2. And we have a rule that says if we have a negative exponent, we can send that to the bottom. And we get 1 over 3 squared, which is 1/9. Now, what a lot of people will do is at this point, they'll diverge from the rules that we have there, and they'll do some sort of logic like this. And they'll say, well, I have 3 to the 18th on the bottom, and I have 3 to the 16th on top, so I'm going to subtract the two numbers. And I'm going to subtract them so that I get a positive number. 18 minus 16 is 2. And then the question is, where do you put 3 squared? And you put it where the larger number was. So the 18 was in the bottom, so you get 3 squared right here, and then you're back to here. So you can sort of skip some of these steps here if you think about it carefully. Example B, x squared times y divided by the cube root of z, all raised to the 6th power, times y times z squared over x to the 2/5 power, all of that raised to the 5th power. All right, well, the first thing I'm going to do is I'm going to give the exponent to all of the parts in the numerator and the denominator. So we have x squared to the 6th times y to the 6th divided by the cube root of z to the 6th times y to the 5th times z squared to the 5th divided by x to the 2/5 to the 5th. Let's simplify. So x squared to the 6th, you multiply the exponents, you get x to the 12th. Y to the 6th stays the same. Now here, the cube root of z is actually z to the 1/3. So we're going to multiply 6 times 1/3, and that's going to give me z squared. Times y to the 5th. Z squared to the 5th is z to the 10th. And then x to the 2/5 to the 5th power is x squared. Now we simplify. If I look at the x's, I have x to the 12th divided by x squared. That gives me x to the 10th. Times, I have y to the 6th times y to the 5th. So that's y to the 11th. You add the 6 and the 5. And finally, I have z to the 10th divided by z squared. So that's z to the 8th. So this is x to the 10th, y to the 11th, z to the 8th. Let's look at example number 2. Solve for x. 3 to the 2x minus 1 power is equal to 1/9 raised to the 5x power. So the key here is to make the bases the same. And we know that 9 is equal to 3 squared. So 3 is going to be our common base. So we're going to use 3 to the 2x minus 1 is equal to 3 something and then raised to the 5th power, 5x power. So the question is, what do I need to do to the 3 in order to produce a 1/9? And the key is that 3 squared is 9, but that would be 9, not 1/9. So how do I get it to become the reciprocal? And it all goes back to that negative exponent rule that says a negative in the exponent moves the term to the other part of the fraction. So in this case, it would move it to the denominator. So we're going to have -2 as the power there. And now let's simplify here. So we get 3 raised to the 2x minus 1 power, and that's equal to the 3 to the -10x power. And now that the bases are the same, we can write an equivalent statement that is based on the exponents. We get 2x minus 1 is equal to -10x. Now, some people like to say, oh, yeah, the 3's canceled. No, that's not quite what's going on here. You have one equation that logically results in the other equation. The threes aren't canceling. There's nothing that you're doing to the threes here in this case. You're just taking one equation and creating another equation that logically follows from that. Sort of a restart kind of thing. All right, let's solve for x. I'm going to move the 10x over. That's going to give me 12x is equal to 1. Let's move the 1 to the right side. And divide by 12. So x is equal to 1/12. All right, go ahead and work the group activity. If you have some partners that you can work with, feel free to do that. Or if you want to go at it alone, since it's on video, you're welcome to do that. What you're basically doing is you're trying to figure out what value this limit is. And why is this limit so interesting? Well, what's going on in this limit is the n value is going to infinity, which means that 1 over n is going towards 0, because as the denominator of a fraction gets larger and larger, and the numerator staying fixed, then the value of 1 over that number, in this case 1 over n, that's getting really, really small. Think about it as if n is a million, a billion, and a trillion, 1 over n is a millionth, a billionth, and then a trillionth, and it's getting smaller and smaller and smaller. So together, those two things say that 1 plus 1 over n is actually approaching 1. And then 1 to any power should be equal to 1, right? No matter how big the power is. And that's what's going on in the exponent here. You're raising it to the nth power. But it's not quite that intuitive, let's say, right? So what's happening is this is getting closer and closer to 1 while still not being 1. At the same time, we're raising it to the nth power. And so something is happening there. It's sort of a battle of two different sides. It's a race to get the inside closer to 1, but you're raising it to these really large powers, and they're getting bigger and bigger and bigger, which we know that makes things sort of blow up. So what's going to happen? Is it going to go to 1? Is it going to go to infinity? Or maybe there's some sort of middle ground number that it sort of settles on. That's your task. You need to figure out what the limit of this actually is. So I would suggest that you use your calculator and evaluate this function. If you'd like to use the table feature on your calculator, you can always change the this to x, right? Change the ends to x, and then change your calculator to independent in the table set. When you do that, you're allowed to just type in any values that you want. Okay. Otherwise, you could just type in each individual value of n and produce the result. You could also use a spreadsheet to complete this, however you want to do it. And then I don't want to give it away, but then there's a question there at the bottom, so you have to sort of answer that. All right, so go ahead and work on that. Pause the video and take a few minutes to work that up, and then see if you can recognize what's going on in this. You need to use at least 7 decimal places on these, and you'll figure that out about why you need to do that when you finish. All right, go ahead and pause the video, and we'll catch up with you after that. Let's look at example number 3. A company sells energy drinks by the case. The price demand function for x cases is given by P of x is equal to 36 times e raised to the negative 0.002 x power. Question A. Find the price per case when 200 cases are demanded. So 200 cases, that's the x. So we want P of 200. It's going to be 36 e to the negative 0.002 times 200. If you plug that in your calculator, make sure the entire exponent is evaluated before you do the e stuff, and you get $24.13 per case. Question B, find the revenue function. Well, the revenue function is equal to x times P of x, number of items times the price, So this would just be x times 36e to the negative 0.002x. And it's customary to put the x inside the number here. So it's going to be 36x e to the negative 0.002x. And part C, find the revenue earned from selling 200 cases. So we're going to do R of 200, and this is going to be 36 times 200 times e to the negative 0.002 raised to the 200. And if you work that out, you get $4,826.30. Next, we want to talk about compound interest. And the compound interest is the interest that is earned when you invest money in an account and it earns interest over a period of time. And then for the next cycle of earning interest, you not only earn interest on the original investment, but you earn additional interest on the interest that was earned. And in this way, it just keeps growing your money because the interest keeps producing more interest. Because of that, the model for compound interest is an exponential function. And you can see the compound interest formula is a of t is equal to p times 1 plus r over n raised to the nt power. So the independent variable here, t, is time. And that acts like the x, and you can see that time is in the exponent. Right? And so sometimes you'll hear investment people talk about, oh, the money is growing exponentially. Yes, that is what they are talking about. This is also the reason why you should start a retirement account in your 20s, because it gives you that much longer for your money to be compounded into something much larger, right? So if you were to start a retirement account at age 20 and you worked until you were 60, let's say, then that would have 40 years of compounding, which is very powerful. And so use the power of compounding to your advantage, especially when it comes to retirement accounts going through time. Now, what do all these variables stand for? Well, A is the future amount. P is the principal invested. That's the amount that you put into the account when you opened it. R is the interest rate, and to use R in this formula, you need to convert it back into a decimal. It usually is given to you as a percentage. N is the number of times per year that the money is compounded, and T is the number of years that the money is invested. Now this N is the one that you need to interpret whenever you get the statement of the problem. If they say that the money is compounded annually, then that means N is equal to 1. If they say it was compounded semi-annually, then N is equal to 2. It's twice per year. Quarterly means that the money is compounded 4 times a year, because quarter. Monthly would be every month. And there are 12 months in a year, so N is 12. And daily is N is equal to 365 days in a year. All right, let's look at an example. Example number 4. Sally invested $500 in an account that earns 3% compounded quarterly. Graph the amount in the account over time and how much is in the account after 8 years. How much interest was earned? So let's go ahead and form the equation for the compound interest. So this is going to be A of t is equal to the principal, 500, times 1 plus the interest rate written as a decimal, so it's 0.03, compounded quarterly. That means n is equal to 4. And the n goes in two different places. It goes in the exponent and it goes in the denominator. And we're graphing it over time. So it's 4 times t, or you can just write 4t. All right, so here's a picture of the graph. And you can see that it is exponential, but it's very shallow. It's because it's only rising at a 3% growth per quarter. And the other thing to note is the graph sort of represents a continuous version of this. It's not continuous compounding. We'll get to that in a moment. But it's really sort of very discrete. And so you don't get all the values in the middle, but when the bank compounds the money, you get those amounts at the end of every quarter. How much is in the account after 8 years? So we do A of 8, and you just plug in 8 for t, and you get $635.06. And then how much interest is earned? Well, interest is money that wasn't yours to begin with. So interest is the amount minus the invested principal. So this would be $635.06 minus the $500 that was invested. So it's $135.06. So it seems to make sense that if the money is compounded more often at the fixed interest rate and a fixed principal and all that, if you compound the money more often, you would get more money, because every time you compound the money, you get a little bit of extra interest, and then that interest is going to gain more interest on itself. So if we compound the money more often, we have more money. So why don't we just compound the money continuously, and then the money should go to infinity, right? Well, not quite. So what actually does happen? So let's talk about continuous compound interest. So I'm going to start with the main compound interest formula. And now we're going to let the n, the number of compoundings per year, go toward infinity. And what that would suggest is that the money is continuously being compounded, just all the time, right? No stop. And then let's write that down. So n is going to infinity so that money is continuously being compounded. All right, so how do we do that? Well, you guessed it, n goes to infinity. That means we need a limit. So we're going to take the limit as n goes to infinity of a of t, and that would be equal to the limit as n goes to infinity of p times 1 plus r over n raised to the nt power. Now, one of the rules of limits is if you have numbers, then they can come out to the front. The variables are the ones that have to stay inside the limit. Well, the p in this case is actually a fixed number, so it can come out to the front. So we can have p times the limit as n goes to infinity of 1 plus r over n raised to the nt power. Now we need to do a little switcheroo here. Now let's let n be equal to k times r. So r is the fixed rate at which the money is being compounded, and we're going to bring in this k. We're going to say that as the n is going to infinity, we're going to say that there's this k that you could multiply by r to produce that n. And with this, since the n is going to infinity and the r is already greater than 0, it's positive, k is going to infinity as well. And now the trick here is to substitute. So I'm going to pick this back up, my limit. We're going to say that this is now equal to, I forgot my p. Let me get my p in here. P times the limit as k goes to infinity of 1 plus r over, and we did have an n right here. Well, that n is now going to be kr. And then we did have another n up here in the exponent. Well, that one is now kr. And all of that is being risen to the t power. All right. So now I'm just going to do a little simplifying here. So we get p is equal to the limit as k goes to infinity of, I'll put this here, 1 plus, I had r over kr, so the r's are going to cancel, and that's going to leave 1 over k. And then I really have these three exponents, and these three exponents are really all multiplied together. It's really k times r times t. So what I'm going to do is I'm going to break off the k and leave it here. But notice that r and t are not part of the limit variables. They're constants as far as this problem is concerned. And so they can go on the outside of even the limit. And so we put them out there. And then the question is, what is this limit? Well, this is the limit that you did in the group work. And hopefully in the group work, you discovered that that was equal to the value of the letter of the number e. And so this is the compound interest formula. It's PERT. And it says that the amount of money in an account when p dollars is invested continuously, compounded, at a rate of r over a time frame of t years, then p times e raised to the rt is the amount in the account. So whenever you have continuous compound interest, you have to use a different formula from the regular compound interest. The regular compound interest formula uses n, which is a finite number of times per year that the money is compounded. Continuous compound interest formula is this one here. Let's take a look at example number 5. Suppose $500 is invested at 3% compounded continuously for 8 years. How much is in the account and how much is earned? So the question was, if we compounded the money continuously, wouldn't that just blow up and we'd all be rich? If that were the case, then there would be tons of people who are just billionaires at this point. So obviously that's not it. The E is a limiting factor. That's why we have a limit. And so it provides an upper bound for how much you can actually earn based on what your principal was invested, what the interest rate was, and what the time frame was. And so here we have $500 invested times E raised to the 0.03. That's the rate written as a decimal again. And then the time frame was 8 years. And this is actually $635.62. And the last one that we had, Sally, same problem, except it was compounded quarterly, only ended up being $635.08. And so the difference is not that significant. It did not blow up on us. We did not become billionaires. And that's just the way it works. So that's the amount in the account. Let's find the interest. Interest is amount minus principal. So it's 635.62 minus 500. These are dollars. And that's $135.62. So in fact, it was only a 58-cent difference between continuous compounding and the quarterly compounding. Our final topic is effective interest rate. So suppose the bank gives you two options for where you can invest your money. One of them is a certain interest rate with a certain compounding time. Another account has a different interest rate with a different compounding time. How do you know which one is the better investment? And that's where effective interest rate comes in. So effective interest rate is the equivalent simple interest rate after 1 year. And it's used to compare different compound interest rates. All right. So basically what you're doing is you're figuring up the interest that was earned after 1 year and comparing those two accounts to see which one would be better. So there's a formula. Let's derive the formula. So basically we let t equal 1. So in case you've forgotten the simple interest formulas, let me give those to you real quick here. So interest is equal to PRT. So the principal times the rate times the time. And then the amount in the account would just be the principal added back to the interest, which is P is equal to 1 plus RT. When you factor out the P. So what we're going to do is we're going to set the simple interest rate equal to the compound interest rate after 1 year. So this would be P times 1 plus RT. I'm going to use a big R for this, and the T is 1, so there's nothing there. And I'm going to use little r for the compound one. So because they are different interest rates, that's the whole point. We have this R is going to be the effective interest rate. Now the compound interest rate for this would be P times 1 plus little r over n raised to the n, and then it should be a t, but the t is 1, so we'll just leave that off. And you want to solve for big R. So the first thing we notice is that we can divide both sides by p, and that tells us that the effective interest rate is independent of how much is being invested. All that matters now is the rate and the compounding period, because the only variables we have left are r and n. So next, we're going to move this 1 that's added on the left side to the right side. And there it is. That's the effective interest rate formula for compound interest. Now, if you have a continuous situation, continuous compound interest, then your R takes on this equation, e raised to little r minus 1. All right. Example number 6. Determine which investment is better, a 3.20% compounded quarterly or a 3.18% compounded monthly. So you might say, well, 3.2% is a larger percentage, so that has to be the better investment. That's not necessarily the case because the compounding times are different. Because you're compounding more often with the 3.18, it could be that the 3.18 is better. You're going to get more money in the long run over a year than you would with the quarterly one. So we do have to do the math and figure this up. It's not as clear cut as one's bigger in the number with the interest rate than the other one is. So let's see. So let's do the 3.2. I'm going to call this big R1. And this would be 1 plus the interest rate, 0.0320, divided by 4, because it's compounded quarterly, raised to the 4th power minus 1. And you work this out, turn it to a percentage, you get 3.2386%. You usually need a lot of decimal places to compare these, so make sure you write out enough decimal places. And then we have 3.18%. I'll call that one R2. And that's going to be 1 plus 0.0318 divided by 12 raised to the 12th power minus 1. And this one multiplied by 100 to produce a percentage is 3.2268%. So it did in fact turn out that the 3.2% investment was the better investment, but they were actually pretty close. They were actually much closer than they started with, as it seems. All right, thanks for watching. We'll see you next time.